Of all the compounds found in our universe, none is of greater importance than water. The chemical composition of water may be shown by the action of a direct electric current upon it. In electrolysis, the two electrodes are immersed in water which contains a small amount of sulfuric acid. To increase conductivity, volume of gas formed at the negative electrode burns with an almost colorless flame. This gas is hydrogen. The second gas formed at the positive electrode causes a glowing splinter to break into flame. This gas is oxygen. You must remember that the 2-to-1 ratio of hydrogen to oxygen, as shown by this experiment, is only by volume and not by weight. The boiling of water may be demonstrated in this flask. Through the stopper of the flask, we place an outlet for the steam, an open U-tube with mercury to serve gauge, and a thermometer. The thermometer is not placed in the liquid, but is suspended in the vapor above the surface. Heat is applied. At first, the air and other gases that are dissolved in the water rise to the surface in tiny bubbles. The temperature, as shown by the thermometer, begins to rise. Soon, bubbles of steam form on the bottom of the flask. Eventually, as the water is heated, the bubbles reach the surface of the liquid, and the water is said to boil. The temperature now becomes constant. Notice that the steam in the flask is invisible to the eye. However, as it leaves the outlet, it forms a cloud or mist. This cloud, commonly but mistakenly known as steam, is actually water which has been condensed by the cool air. Now let us partly close the steam outlet. The confined steam builds up a pressure within the flask, as shown by the U-tube. The boiling point increases as the pressure becomes greater. It is apparent that an increase in pressure causes an increase in the boiling point. We now remove the burner and allow the water to cease boiling. A vacuum pump reduces the pressure, as shown by the U-tube. Once again, the water boils, this time at a temperature lower than the original boiling point. Lessening the pressure always lowers the boiling point of a liquid. The Liebig condenser is a glass tube surrounded by a water jacket. The circulation of cold water is necessary to maintain a low temperature within the condenser tube. The container at the left is a distilling flask. In the top of the flask, we have inserted a thermometer to measure the boiling point of the liquid. The invisible water vapor or steam moves into the Liebig condenser, where it condenses into drops as it is cooled by the circulating water. The liquid from the inner tube is called the distillate and is free from all non-volatile impurities. Let us take a glass of cold water and allow it to reach room temperature. The solubility of gases decreases with an increase in temperature. 1 hour passes before we again examine the water. We note that bubbles of gas have formed on the sides of the container. These bubbles are formed from the air that was originally dissolved in the water. Fish are able to live because of the dissolved oxygen in water. They have no ability to separate the oxygen that is chemically combined with the hydrogen. When we relieve the pressure in this bottle by opening it, the gases dissolved under pressure are released. Solutions may consist of 2 or more liquids. To illustrate, let us pour some water into this container. Now, let us add some alcohol to the partially filled beaker. You will note that the liquids appear to dissolve in each other. The alcohol and water are mutually soluble. Such liquids are said to be miscible. Not all liquids, however, behave in the same manner. Let us pour some oil into this cylinder. Now, we add water to the oil in the cylinder and observe that the results this time are quite different. The liquids do not mix. Layers are formed that persist even though the mixture is stirred. Liquids which are not soluble in each other are said to be immiscible. Temporary suspensions of immiscible solutions are emulsions. Salad dressings are forms of such emulsions. The cleansing action of soap is due in part to its emulsifying properties. Let us consider the solubility of solids by stirring copper sulfate into water. The solid copper sulfate dissolves in the liquid, forming a clear solution. The water or any other substance doing the dissolving is the solvent, and the substance dissolved is the solute. Eventually, we reach a point where no more solute can be dissolved at that temperature. We now have a saturated solution. We evaporate part of the solvent, and almost immediately crystals of copper sulfate are precipitated from the solution. Here you see them forming on the sides of the container as the water is evaporated. If the evaporation takes place very slowly, the size of the crystals is increased. The crystals have the definite shape of geometric figures. We may separate the crystals from the solution, called the mother liquor, by a filtering process. The contents of the dish are poured on a filter paper suspended within a funnel. The solution, which is still saturated with the solute, passes through the filter and is now called the filtrate. The crystals, known as the precipitate, are held on the filter paper. Almost all solid materials are more soluble in warm water than in cold. Here is a test tube filled with a concentrated solution of potassium nitrate. The tube is cooled by a stream of running water. The solute crystallizes out of the solution as the temperature is lowered by the water. After the solution becomes saturated, due to the lowering of the temperature, any further cooling causes crystallization. The solvent at the end of the experiment is still saturated. Not all compounds react in this way. For example, if we drop a small seed crystal into this solution of sodium thiosulfate, crystallization takes place immediately. When crystallization once starts, it continues until the solvent is once more merely saturated. There is a decided increase in temperature during this process of crystallization. The weight of 1 cubic centimeter of water, the size of the cube you see in the hand, is the standard of weight in the metric system. This volume of water has a mass of 1 gram, the basic unit of weight. A common unit of volume is the liter, which is approximately 1 quart. It contains 1,000 cubic centimeters. 1 liter of water weighs 1 kilogram, or 2 2/10 pounds in English units. The ratio of the weight of a substance compared to the weight of an equal volume of water is called the specific gravity. The hydrometer is used in comparing the densities of liquids. Solid materials, such as this cylinder, are sometimes weighed in air and in water to determine their volumes and densities. Energy changes in the form of heat play an important part as water changes its physical forms. Ice is added to the water in this test tube, and a thermometer is inserted. The ice begins to melt. The temperature drops to 0 degrees centigrade, which is the freezing point of water. It is apparent that heat energy must have been absorbed in the melting of ice. The cooling effect in an icebox is due only to the melting of the ice crystals. Now we insert a test tube of water into a freezing mixture. The temperature falls even below the 0 reading. The tube is shaken and the water quickly freezes to ice. The temperature rises rapidly. This energy that is released when ice is formed and is absorbed when it melts is the heat of fusion of water. Careful experiments, such as this one, show that the heat of fusion of water is about 80 calories. A calorie is the amount of heat needed to raise 1 gram of water 1 degree centigrade. Equally important are the energy changes involved in the relationship of steam to water. Experiments of this type show that the heat of vaporization is about 540 calories. The steam heating plant is a common application of this important principle. Water is changed into steam in the boiler of this heating plant as heat is absorbed. In the radiator, the steam is condensed back to water, releasing heat energy which warms the room. You have seen some of the more important chemical and physical properties of water. In a further experiment, study and discuss this most important of all compounds.